I'm delighted to welcome Briana Morrison all the way from the University of Nebraska, Omaha. It's so lovely that we're online and we can have friends and colleagues from all over the world come to present on these seminars. And the topic today is Subgoal labels, part of reducing cognitive load in introductory computer science education. So you can share your screen.
All right. Well, thank you so much. So thanks to the Raspberry Pi Foundation and to Sue and Diana for making this all possible. I think in this time of the pandemic that this is just amazing to be able to have this kind of seminar where people that are interested in computer science education can actually get together and discuss things. Being that we're no longer going to conferences, I think that this is just fabulous, and I thank you very much for inviting me. So today I'm going to talk to you about subgoal labels and how they can reduce the cognitive load in introductory programming. But first I want to do some acknowledgements, and that is that most of this work was done with my colleagues, Lauren Margelot and Adrian Decker. Lauren is at the Georgia State University and Adrian is at the University of Buffalo. And I could not have done this without them. I highly recommend collaborative research work. It helps me to stay on task and makes me accountable to others. And I am much more productive when I am working with others than I am by myself. So today I will be talking to you about first cognitive load and what cognitive load is, and then how we have used the notion of cognitive load to recommend how we might improve student performance and student learning. And I have some really exciting results to share with you towards the end. So cognitive load is what we would call a threat to actual learning. And as educators, we're interested in helping our students learn. And that means we need to be aware of the things that can impede that learning, one of which is too much cognitive load or too much cognitive overhead. So John Sweller invented the idea of cognitive load theory in 1988. He is an Australian educational psychologist and is actually based upon the brain architecture. So the notion is that we receive information from our senses, some of which we immediately forget. Most of you may have seen the spot the gorilla in this video kind of a thing. If you haven't seen it, then you should Google it because it's amazing. And you will not believe the results when you're all done with it. The others that we come in through our senses then go into our working memory, some of which of that we also forget because basically the working memory is limited, right? It's limited in the number of items that we can store and the duration of how long that we can actually store it. Then from there, it then transfers to long-term memory. This is where the learning actually occurs, right? And we produce what are known as cognitive schemas. These are the information that store and organize the knowledge that we can then recall when we need to. So the cognitive schemas themselves are actually hierarchical in nature. They incorporate multiple different elements of information into a single thing, which we call a chunk, right? And the idea is we don't think about retrieving this information. It is automatically retrieved as our brain signals through different synapses which information that we want to retrieve. So we're not saying I want to go look for this information specifically. Something occurs within the stimulus input that then says, oh, that triggers this, which means I need to go look at this information. So we're interested in what happens when or how to get information to that long-term memory and incorporating schema. So we say that learning actually occurs when one of four things happen. Either when we create a brand new schema, so we have this hierarchical nature and we say, it doesn't really fit into anything that's there, so let's create a new piece of information and understanding this. Or we have what's known as assimilation, and that is we learn something but it fits into an existing chunk that we have. Or we might have elaboration, which is when we combine things into a larger chunk. This is where abstraction and generalization would occur. Or we have what's known as accommodation. And that's when you have a misconception and then you view that misconception and you realize, oh, I had a misunderstanding of how that works. And so a larger chunk would be broken down into smaller chunks, and it's a conceptual change, and you're restructuring the entire network. So that's a brief overview of human brain architecture and how the information gets in. Now, where does cognitive load theory fit in, right? So imagine that your working memory is like a cup. And as we are receiving all of this information, and some of it's flying out of the sensory modes, and some of it's going into working memory, and then we're trying to put all of this information and what's being retained into working memory, and it's like pouring information into a cup. However, when you have too much information in that cup, then it overflows, right? And this is what we call cognitive overload. So we know that working memory is limited in the number of things that we can hold. If you want to go by Miller, it's plus or minus 7. If you want to go by Cowan, it's plus or minus 4. And we also know that the duration is limited to about 30 seconds without actually trying to work on memorization of it, right? So you have approximately 30 seconds to put 4 to 7 pieces of information in your working memory before it can go into either long-term memory or before it overflows. Now, the question is, what are those 4 to 7 pieces of information? What are those individual chunks, right? And this becomes the difference between a novice and an expert, and it's the size of those actual chunks. It's what it is that you store in memory. I like to, the analogy that I usually give about cognitive load theory and cognitive overload has to do with if you're teaching someone how to read, right? Very young students, when they're learning how to read, we teach them the individual letters, right? And then you put those letters together in a word. And if it's a word they haven't seen before, they're still looking at the individual letters. So each individual letter would be a token or a chunk that they're then trying to assimilate or create a new schema for what that entire word is. Once you become a more fluent reader, then you look at words and you are no longer looking at the individual letters. You just recognize the entire word. So then your chunk becomes a word. After you become a quite fluent reader, we know that we can even decipher the information when the letters are all mixed up, because our brain does pattern matching and automatically retrieves the word that it thinks it should see, even if the letters are mixed up. And we have much larger chunks that become more like phrases. You can read an entire sentence and then not remember the individual words that were in the sentence, but only the meaning of that sentence. So that's kind of how it goes from novice to expert in terms of what it is that you can remember at one time. So I'm interested in applying cognitive load theory and subgoal labels to learning how to program, right? So let's look at a typical programming example. So this might be a typical exam question that you would get in the middle of a Java course, right after you had been taught control structures, right? And so look at this typical example and think about what information does the student have to know to be able to interpret or actually solve this problem, right? What are the pieces of information that the student has to keep in their working memory in order to solve it? And where might the information overflow? Obviously, there are many different pieces in this, which is one of the reasons why instructors for ages have said, let's use distributed cognition. Let's please use a piece of paper. Please write the information down. Please trace this, right? So that you are not trying to hold all of this information in your head, because typically you would make a mistake, right? Especially if you're just beginning into this larger chunking phase and you wouldn't get it. Think about the student who is still trying to parse what an assignment statement means, right? They're still looking at the individual tokens of what is the data type, what is the variable name, oh, this is a value. How do I get this value into this? And then you get down into a loop, and imagine the overload that that poor student's brain is going through when they're trying to handle all of those different pieces of information. So that's where we want to reduce the load, especially for those novice and beginning learners. One of the ways to do this is through worked examples, right? Worked examples describe the solution process to a user or a learner who is very new in or a novice in the solution or problem solving process. So here's an example from algebra. Worked examples are a type of instruction where we teach the procedural problem solving process by giving learners concrete examples of what it looks like. We have been doing this in math for ages and ages and ages. It's the example of the procedure to solve the problem, the explicit steps that you're taking, and notice that it is the process, not just the answer. So a little bit on my soapbox here, a side note. This is typically what you would see in any math or science textbook. Now think about your computer science introductory programming textbooks, right? They present the problem that says we're going to write a program to do X. And then what is the next thing that you see? Typically, it is the finished program. It says, here you go. This is what the result would look like. That is not a worked example because it's not showing process at all. It's just showing the final answer, right? That is not what we want to do with worked examples. We want to say, what are the step-by-step ways that you can get from problem to solution, right? So on that previous worked example, what do you remember from the slide, right? Other than me going off on a little bit of rant about stuff, right? So you probably remember that there was some math, and most people remember that there was a Lamborghini, right? So those are the two things that you take into your brain, right? Instead, worked examples are good because they show this step-by-step demonstration of how to perform a task or solve the problem, but they are also poor because they have to include specific details that are specific to that problem that then make it very difficult for the learner to be able to abstract or generalize that problem-solving procedure. This is where subgoal learning comes in to help. So in order to minimize the bad parts of worked examples, we introduce subgoal learning or subgoal labels to be able to allow students to generalize the problem-solving process. So the subgoal learning framework has been used in programming and other fields to break down this procedural problem solving into much smaller pieces that the novice can grasp much more easily. Given the subgoal labels, or when we provide worked examples with subgoal labels, it improves the learner performance while they're solving novel problems without actually increasing the amount of time that the learner actually takes to spend studying on the information or solving or working problems. So when the people or when students learn using subgoal labels in the problem solving process, they basically have better retention and they're able to transfer that knowledge to other problems. So let's look at what they look like. So in this is an example of using subgoal labels within the algebra domain, right? And what we do is we group steps together and then apply subgoal labels within the overall problem-solving process. And we identify those steps in the problem-solving process. The subgoal learning framework works a bit like this. You create your overall subgoal labels by grouping steps together within the problem solution, and then you want to give those steps some sort of meaningful label in order to highlight the problem solving process. The subgoal labels themselves should provide organization to the solution process, and it allows the learner to chunk those different steps into memory. By studying multiple sub-goal labeled worked examples, it allows the learner to decontextualize that specific example, which leads to improvement in transfer and solving novel problems. So this was actually discovered, or the initial work done on it was done by Richard Catronbone, who is an educational psychologist at Georgia Tech. And he discovered in 1998 that the shared functional features of working examples can help the learner to organize the information into their own brain. It basically gives them a recipe or a step-by-step process for how do I go about this problem-solving procedure. It also can lead to what we call automaticity. Okay, so here is another example, right, where the sub-goal labels have been provided. And this allows students to see the process with names to those steps in the process as they go about learning. So learning with sub-goals has been studied in many different STEM disciplines, algebra, geometry, statistics, chemistry, and biology, just to name a few. And there are many studies that compare novices who look at worked examples with sub-goal labels followed by doing practice problems, and the amount of time that they spend studying and solving those problems is equal to or less than the amount of time that students would do just solving an equal number of problems. And they typically perform better on then retention, how much they retain, the knowledge that they've retained, and on their accuracy, in other words, how well they solve the problems. So the number one question that I get is, what is a sub-goal? What does one of these things look like, right? So it's not an individual step in the process, and it's not the overall solution. It is the intermediate steps that lead to that. And a good sub-goal label should describe that function or goal, and it should convey what it is that the steps are in, that it groups together want to achieve. And it should help the learner connect the steps to their overall purpose. You typically want them to be an action-based phrase, and they want to indicate to the learner what is the next step in the problem-solving process. So a lot of computer scientists especially get used to having these things as comments in their code. And you may have done comments in your code. So they are not explicitly comments, but they could be comments, right? So generally when we tell students to write a program, we ask them to add the comments, and the comments are typically what it is they're doing in their next little set of code, right? What 3 or 4 steps does this accomplish? And we want to abstract it up to a level that says, let's generalize it. That could be a sub-goal, but it's not necessarily a sub-goal. And the difference has to do with whether or not it applies to this specific program or whether or not it could be generalized across problems. So in this particular example, the sub-goal would be to define and initialize variables, but the comment may be initialize the tip variable, right? So the tip variable is specific to a problem versus define and initialize is generalized across multiple problems. So what did we do? We wanted to look at sub-goal learning specifically within programming. We know that previous work has been done. It's been done with block-based programming. We've done it with text-based programming, and we've done it with K through 12 teachers. But in each one of these cases, it was done in a lab environment, very controlled, where we brought people in, said, do these problems in a lab, thank you very much, and you may leave. What we wanted to do is say, what happens when we do it in a bit of the wild system? And we wanted to study when it was done not with a single topic, but across an entire course and done within the classroom, not in the lab environment. Okay. So first thing I want to do is, we've had enough sitting. Now it's time for some active learning. right? So I want to see everybody do this. This is going to be great on Zoom, okay? So step number 1, I want you to rub your belly. Just in a nice circle, just rub the belly and keep on doing that. And while you're doing that, now I want you to tap your head. Okay, do you find it difficult or hard? Right? Most people have to actually think about the actual motions. If I asked you to do one or the other, you would have no problem doing it. It's very simple. When I ask you to do both at the same time, then it becomes my brain has become engaged and I actually have to think about it, right? Now I want you to take, okay, maybe not a minute, maybe 30 seconds, right? And think about how you would explain to someone how you ride a bike or how you tie a shoe. Anyone who is a parent out there knows that these are 2 things that you typically try to teach a child, and it's probably 2 of the more difficult things that you have to do, right? Explain how you tie your shoe to someone, right? Typically, it's very difficult, and why that is something that we call automaticity, right? You don't think about tying your shoes, and you don't think about riding a bike. You don't think about driving a car. It just becomes automatic once you've crossed a certain threshold and you become so proficient at it. Your brain no longer actually has to work at thinking about it. It just becomes automatic to do, right? This is one of the problems that we have as instructors. Many things to us have become automatic, and we therefore cannot articulate that to students who are not proficient. We literally have forgotten what it is that we learned. So we have to be able to stop and think about it and try to make that knowledge explicit in when it is that we're teaching. That's one of the things that Subgoal labels attempt to do. So what we did, we started with thinking about if we were going to apply this to an entire course, what topics would we want to tackle, right? And that we would want to define for using subgoals in CS1. So we did a review of textbooks and we looked at them, and this is what we came up with, that there are topics, general topics that are taught in most CS1 courses that are using a procedural programming language. So these are the ones that we currently have subgoals for. The next thing that we did was known as the TAPS protocol, which is the task analysis by problem solving. So there was a subject matter expert, that was me, and a knowledge extraction expert, and that was Lauren. And we focused on problem solving, not teaching. So literally the 2 of us sat around my kitchen table for a week. We had a whole bunch of textbooks around us and we would pick the topic. We would go to the problems in the back of the textbook and I would begin to solve the problems, right? Notice at this time, Lauren had no programming experience. So she was a complete novice. As I started to solve the problem, she would ask me questions like, why did you do that? Why is this the next step? Why is this piece of information here? Why did you have to declare this variable? Why did you put a loop here? And I literally had to think about why I was doing each particular thing. We did that until she was comfortable with the problem solving, and then she would attempt to solve the problem or another problem. And I would be, then I got to play teacher and say, nope, you don't do this. This is the next part. And she'd say, well, why is that the next part? Why is that the next step? And after we had done this for all of these different topics through, like I said, a week at my kitchen table, we started to define and figure out what the steps were for the subgoal labels. Now, since that initial classification, we've updated them probably 3 or 4 times. And we are not here to say that this is the only set of subgoal labels for doing intro programming. And we're not even trying to claim that they are the best set of subgoal labels for doing programming. We just know that they are a set of subgoal labels. So here is an example of 2 of the things that we did. For most of the topics, we divided it into 2 separate tasks, one of which is evaluating, which is typically what we do on exams. And the other is when you're actually writing one of those kinds of statements, which is typically what we ask them to do then in a programming assignment. So for evaluating a selection statement, there are 3 subgoals. For writing a selection statement, there are 6 subgoals, right? And the idea is we've tried to break down the individual steps of what a student would do when they want to do one of those. So now we've defined all of them, and later I will show you where all of them are available to you so you can have access to them. And then once we have them, then of course you have to study them. So in the fall of 2018, at my university, we were fortunate enough to be able to have an opportunistic study in the sense of we had 6 sections of our introductory programming class. I was teaching 2 of those 6 sections, and we had 2 other instructors that were teaching the other sections. It is a flipped classroom model where the students watch information on video before coming to class and have to post in a discussion forum. We come to class, we lecture by doing worked examples in class and providing peer instruction questions. And then we go over the answers of those peer instruction questions and do live coding. We were using the exact same slides, the exact same peer instruction questions, the exact set of TAs. In addition to the lecture, they also have a 2-hour lab that they attend, and the labs are mixed up from all the different sections. So a particular lab might have students in it from all 6 different lecture sections. We were using the exact same quizzes. Quizzes occurred over the weekends. They were released on Friday mornings and due on Monday evenings. They were done online. We used the exact same exams. We used the exact same lab assignments and the exact same regular assignments. So the only difference that was done is that in my 2 sections, I introduced subgoal labels. I did this in the classroom and took away some of the worked examples that the other instructors were going through. And instead, I would present the subgoals and then work through the subgoal label worked examples that were there. And then I would have practice problems for them where the subgoal labels were labeled at the top of the practice problems. And as they were working through the practice problems, I would encourage them, what subgoal are you on? What's the next step? And that sort of information. So those were the only differences between the different course sections so that we were able to collect the data. So the first thing that we did is that we looked at the results on the weekly quizzes. So there were 15 of these quizzes. We looked at 2 different scores. So one is we called it the total score, and that is all of the quiz scores, including those who earned a 0, so they didn't do it. Then we looked at what we call the average score, which excluded the 0s or those that didn't do it. The result was the students in the subgoal sections, both of those sections, scored statistically significantly better than those in the control section. So we were going, oh, this is good. Subgoals help. That's awesome, right? The other thing is that the subgoal group consistently performed better on each quiz. So it wasn't just like a one-time quiz that was one-off. It was every one of the 15 quizzes the subgoal groups performed better on. Then we looked at the exams. So there were 4 exams. They were all done in an online environment, but they were in a supervised lab. So the students come into their lab session, log in, and take their exams there. The exams are actually based on, there's a test bank of questions. So whatever the topic is, there might be 5 to 10 questions, and we say choose 3 of them. So the students are actually getting random questions within there. Where we try to assume the difficulty is similar, but you know how that works, right? So what we discovered was that the subgoal group performed better for the total, but it was a very small effect size. For the average, and that's, remember when we take out the 0s, there was no statistical difference between the groups. However, we did note that the Subgoal group had a lower variance within them. In other words, they performed more similar than the other. The Subgoal group did take more exams than the non-Subgoal group, which is going to lead to another finding here in a second, right? So we did some additional data analysis where we took 4 of the quizzes, and these were 4 quizzes that, in addition to the multiple choice answers, they also had what we called an explain in plain English question. The students had no training on explain in plain English questions, not in the Subgoal group, not in the other group. This just came out of nowhere. Note that these explain in plain English questions did not count on their score, their quiz grades, but they didn't know that. Basically, if everyone answered it, they got to put anything down. They got credit for having answered it. So it didn't go into their quiz averages on whether it was right or wrong. But then we did analysis using the solo taxonomy that was developed by Biggs and Collis in '82. For the results, the Subgoal label group gave more complete answers. They often included more relational or abstract information on 3 of the 4 quizzes. There was one quiz that was just used nested loops and everybody was just way off. It was a bad choice to analyze. So, and then on the solo taxonomy itself, they demonstrated a higher level of cognitive understanding and the understanding of the programming principles. So we were really pleased and said, this is awesome. It helps them on their quizzes. And oh, by the way, we think they know more, right? Based upon the solo taxonomy. Then we went to and we identified what we called risk factors. So we wanted to look at the demographic background of the students that were there. What we noticed is that looking at potential risk factors, there were no learner characteristics, which these are the learner characteristics that we gathered, that correlated with the solo scores whatsoever, right? So this suggests that because there's no covariance between them, that the learner characteristics themselves account for the different variance in exam performance, right, than the solo scores. So what we believe is that it's truly the subgoals that are making the difference in what we see in the quiz grades. Then we wanted to examine what happens with the students that we generally consider most at risk. So the students who are most at risk, we looked at those who said, I expect this difficulty, the difficulty of this course to be, I expect this course to be difficult, right? We looked at those who had college GPAs that were below average, and we looked at younger students. And one of the reasons that we looked at younger students is my particular university has a great deal of non-traditional students. And we think that older students probably have better metacognitive skills and know how to study better over time. And so we wanted to compare those that were younger versus those that were older. What you can see is the students in the Subgoal group typically performed better, right? Or had about the same difference in where they considered how they performed on the exams versus the control groups, right? So if you look at all of the students who expected the course to be difficult for them, and then you look at the Subgoal group average exam was a 74 versus the control group average exam was 67%. These, by the way, are statistically significant, right? So we looked at those who had expected difficulty, those that had a college GPA that was below average for the course, right? And then the younger students. What we discovered is that students who didn't complete all the exams or had an average exam score below 70, so those would be the ones that we would consider most at risk to not finishing the course. There were approximately half as many students in the Subgoal group versus the control group that fell into that category. In other words, those in the Subgoal group that we would consider at risk persisted to the end of the class. If we look at just the exam average and don't take into account who took which exams, the students in the Subgoal group were half as likely to withdraw and half as likely to fail. So these two slides, right? When I said earlier that the quiz performance made us happier, right? Remember that we said that they did better on the quizzes. The quizzes were a measure of the knowledge that they had learned that week versus exams is over a much longer period of time where it wasn't as statistically significant, right? So they're doing better on a weekly basis, and we know that if they thought the course was going to be difficult or they had poor GPAs or they were younger, they performed better on the exams and they stuck it out through the course. So this is what we think is the most exciting about the Subgoal labels, is that it has a tendency to help those most in need or most at risk. So that's what we're excited about. So in terms of the future work, we have what I call rinse and repeat, which we repeated all of this in fall 2019, 5 sections, all the different instructors. And this time we asked everybody to introduce the worked examples and the Subgoal labels. That went for about 3 weeks, and the other instructor said, I'm not comfortable introducing Subgoal labels, you have to do this. So I went and then recorded videos, and then we said, students, please watch these videos before class. Guess what they didn't do? They didn't watch the videos. So,
Briana, do you want to?
yeah.
Briana, do you want to wrap up in a minute or two? Yeah.
I do. Yes.
Thanks.
So that I have 2 more slides. So that's the idea. But we're still analyzing that data. What we have now that I can show you is that there is a website that has all of the information for our Subgoal stuff. And what we have done in spring and what we're doing this summer is we are transferring all of this to an ebook. So you can actually go to the ebook and look at our worked examples that have both text and video. We have practice problems that will be auto-graded, and we're implementing assessment. If you want to sign up for this, the course that you need under the Runestone platform is called Subgoals with a capital S, and it is ready for use and adoption for fall 2020. I will plug that it's great for remote instruction. If you want your own course that you can follow through and grade your own students and have your own instructor dashboard, just email me and we can set you up for your own course, okay? And then I'll tell you that we have a bunch of future work, but that we'll get into that for the questions. So, all right, my conclusion is, hey, Subgoal labels are beneficial, they're good, they help students on quizzes, and they help the most students who are most likely to need the most help. So, thanks, that's it. Questions?
Excellent. Well, Briana, thank you very, very much. I think we can all just do our jazz hands, clap, clap, clap. Thank you, whatever we normally do. But what we do now is go into breakouts, which we're a little bit over time, so we'll do a sort of short 7-ish minutes breakout, shall we? And then we'll come back for questions. Welcome back, everyone. So, as we would normally do, if you've got a question for Briana, can you use the reactions down the bottom to wave either of those 2 hands, and we'll do questions that way. Or if you've got a question, you can write it in the chat, but I would rather I'll then ask you to say it, ask Briana directly. So whose group had the first question? There was a lot to, oh, Hayley, thank you. Hayley?
Hi, yes, thanks, Brianna, for a really interesting talk. We had a really lots of questions actually, but I was just going to combine a couple. One of which was about the two groups, the control versus the intervention group, I suppose. We weren't sure if you talked about how similar that they were to start with. I know all the other teaching and everything was the same between groups, but did you have any comparison of what, like the gender composition of the two groups and things like that, and also if what prior knowledge two groups had, and did that have any effect on how they did in terms of the sub-goal learning? So I'll leave it at that.
You're on mute, Brianna.
Thanks. So yes, I was getting towards the end, so that was a little bit skipped over. So we did look at the characteristics between the two groups. There was an initial survey that we asked them for some of their demographic data, like gender, ethnicity, was English their primary language, since that was the language of instruction. We also asked them about prior programming experience and what they had had. What we found is there was no statistical difference between the two groups. So as we considered them pretty much homogenous, since it was the students signed up for the classes based upon random, whatever variables students used to sign up for classes. And we didn't assign them to any particular group. So we consider it to be quasi-experimental since it's not completely random, but we did look at the differences between the two groups in their word tuning. So including in prior knowledge.
Great, thank you. Is that okay, Hayley? Does that answer your question? Excellent. So we'll move on to another question. So Catherine, what was your group's question?
Oh, we had lots of questions. I'll pick out one, and then if anybody else in our group wants to follow up with another one, please go ahead. But one of the things we were interested in is obviously this research is focused on attainment and achievement and understanding. I know you touched a little bit on the effects on persistence and sort of that kind of area as well. We were wondering if you'd done any sort of further research into the impact on attitudes and motivation, and whether students perceive this to be a valuable tool for their learning as well.
So we have not done as much in that area as I would like. We did do an end of course survey, and then we did a follow-up survey during the next semester where students had presumably, if they were majors, had gone on into the second course. And so we wanted to ask them, how did their sub-goal learning compare to now that they're in the next programming class that didn't have sub-goal labels? How did it compare to that? And it turns out we had very poor response rates, and most students said they did not like the sub-goals, and they thought that they were extra stuff that they didn't need. So that's what I can tell you. It's a little bit like broccoli and spinach. It's good for you. So there it is. So, but we would like to look at that more.
Great. Where's another question? I'm scanning the wall for waves and hands and oops. Brian, BT, you've got
Hello.
a question.
I do. Our group was wondering about how long the scaffold, like if you know how long this sub-goal should be used as a scaffold, and whether it should be continued into CS2 and subsequent courses, and how the sub-goals and design patterns may change across that, or whether students internalize those patterns and no longer need it.
So yeah, so they do actually internalize them, but they sometimes get reintroduced when we bring up a new topic. So for example, when we are teaching arrays, which tend to be at the end of the semester, we revisit the assignment or expression evaluation, because now we're dealing with array elements, but we bring back the assignment sub-goals to show them that it's the exact same sub-goal that apply when assigning array elements as it did with individual primitive elements, or even when we're doing objects and object references. So what we find is they will internalize them, but then when we introduce a new topic, we can show them how we can pull some of the previous ones there. And yes, they do actually internalize them. And I know this from having done it in class when we would get to the, and I would say, and what's the next sub goal? And you could see them all going, like this. So yes, they did get to where they were truly internalizing them.
Great, thank you. And there's a question in the chat: how can a teacher design sub goals efficiently by themselves?
So yeah, so if you take a problem and you break it down into individual steps, and then you try to name those steps, and then try to take 4 or 5 different problems and see if the sub goals apply across those problems. That's what we had to do, and that's where the most of our adjustment would occur, when we realized that, oh no, this doesn't really generalize across the problem. We need to find a way to reword this or change the specific sub goal. So the key is defining those sub goals and then getting them to generalize across problem statements so that they are reusable. And I have had people that have done it in other courses. So I know one who did it in a programming languages course, and one who did it in a database course. So.
Excellent. Another question? I'm scanning again. Wave at me if you have a question. Haley, you had it. Oh, Jane's got a question. Hi, Jane. You're sort of slightly dark. I can hardly see. You've got much light in your room there.
Backlighting. Hi, Briana. I absolutely love your research, and thank you ever so much for sharing it with us. I was just wondering, when you're talking about them being steps for problem solving, do you think you were spotting concepts and design patterns rather than skills to work out what the next thing is? And I don't know if that makes sense. So
I'm not sure I understand the question.
So it's associated with problem solving. So when you say it's this chunk of code, that chunk of code is representing a design pattern or a concept, or a, rather than that's the skill to work it out. So it's kind of like like you say, it's more like these are the building blocks that then they might reuse. So is that right?
Yes, and if you have any ideas on how we can tease those two apart, I would love to know. We've thought about this for a while. Currently, we have no sub goals on any of the assessments that we're giving. So there are no sub goals on any of the quizzes or any of the exams that they take. We've thought about so like this fall, when we all are introducing sub goals, what if on a couple of the problems that we asked them to solve, we actually gave them the sub goals and said, please fill in the code underneath those sub goals. So then it wouldn't be quite so, they wouldn't have to internalize all of that at once to see if there is a difference between the two. Our eventual goal is to get the sub goals embedded within an IDE, right? So that when students go, oh, I have to write a loop. I don't know how to write a loop. What are the steps to writing a loop? And they just pop up the sub goals, right, as comments into the code, and then they can just fill in the individual steps that are there. That's when we have the idea that sub goals will actually be most helpful, is when they're constructing programs as opposed to just evaluating these things on paper.
Cool.
Okay,
thank you.
Thank you. We're almost out of time. I've just got one more question. So you talked about doing this at university level, you know, so a lot of people in the audience are, you know, K-12 school educators. Have you got research evidence around sub goals and worked examples in K-12?
We do have it. We actually implemented sub goal labels in code.org CS principles in their introduction of turtles. So it's a block-based language, but we introduced sub goal labels there. And that paper is about to be published, hopefully this summer, later this summer, right? And we will, so that will be out. And it showed, because of restrictions on data and stuff, what we can tell you is the kids who were taught with subgoals had better answers and answered more questions than those who were without subgoals. So that's what we've done in the K-12 space, and it would be great.
Great. Thank you. Well, I'm afraid we've run out of time for questions, so can we just do our thank you to Briana, wave hands, whatever. Look at those waving hands. Thank you very much again. But please do, if you had a question that wasn't answered, please do continue the conversation on Twitter. We'll be sharing the video on the seminar webpage shortly, and a blog post and Briana's slides, so you can be able to follow that. As we said, we were recording, so if you asked a question and you don't want to be in the recording, please email research@raspberrypi.org so that you can let them know that you don't want to be in that. Other than that, we've got our feedback form as normal. Please sign up for our research update, and thank you very much for coming along.